Hello everyone. This is a session on survival analysis. This is a different way of analyzing data that are generated from cohort studies. In this session, we'll introduce the core concept of survival analysis, which is a key method in epi and clinical research when time is an important component of the outcome. So by the end of the lecture, you should be able to understand what survival analysis is, how it differs from standard outcomes. We will also learn how to generate and interpret survival curves, particularly using the Kaplan-Meier method. And finally, we will introduce Cox regression, which allows us to examine how different factors influence the time to an event. So overall, the goal is not just to know the method, but to understand when and why to use them. And to understand why survival analysis is important, let's look at some examples. Instead of asking a simple question like what proportion of person would survive after 30 days, survival analysis allows us to ask a more informative question such as how long do patients survive? For example, in cancer study, we may want to compare survival time between patients with different level of social support. Or we may examine how long it takes for a disease to progress or for a patient to recover after surgery. So this is all the time to event. So the key here is that we are not just interested in whether an event happens, but when it happens. This slide shows a real example from the literature, and this is a study on obstructive sleep apnea and risk of stroke or death. Participants were followed up over time until either the event occurred or they were censored. To analyze this type of data, they used the Kaplan-Meier method to estimate survival and compared groups using statistical tests. So this highlights how survival analysis is widely used in real-world epi study to track outcome over time. And the graph illustrates this survival analysis. So you see that the graph that consists of on the y-axis is probability of survival, on the x-axis is the year, the year or the time of follow-up, and then at the beginning we have those patients who were followed up. At the beginning they were diagnosed either with obstructive sleep apnea or not, so these are the control, and then the patient with the syndrome, and then they were followed up in time to see whether they would die and stroke or when they would die or develop stroke, and comparing the two survival curves. So these are the survival curve, and this P is the significance of the difference between the two survival curves. So why survival analysis? Why do we need it? So the key reason is that many studies, time is a critical dimension. So not all individuals are followed up the same length of time. Some may not experience the event at all during the study. So traditional method like logistic regression, they ignore timing, and linear regression cannot properly handle incomplete data. So survival analysis solves this by incorporating both the occurrence of the event and the time until it happens, while also accounting for. So survival analysis refers to statistical method used to study time to an event. So the key feature is that follow-up time is often unequal across participants. Some individual may experience the event early, other later, and some not at all. So censoring and what we call censoring. Censoring is one of the most important concepts in survival analysis. It occurs when we don't know the exact time of the event. For example, if a participant drops out of the study, or if the study ends before they experience the event. And even though we don't know the exact event time, we still know that the event did not occur up to a certain point, and this is actually very valuable information. So survival analysis are specifically designed to make use of this partial information, so the time that we observe that participant, which is something standard statistical method cannot handle properly. Moreover, when we include all individuals in the analysis, even if their data is incomplete, this helps preserve the sample size and avoid bias. Now, there are different types of censoring, but the most common is right censoring. So in right censoring, so here is the right censoring, 1, 2, we know that the event has not occurred up to a certain time, but we don't know what happens afterwards. So in participant 2, this person might have and we can observe, particularly we can investigate. So some people might have the event, but later after the study, and or they can continue without having the event. Right? Left censoring is the opposite, where we know the event occurred before a certain time, but not exactly when. But this is also something that we don't usually use a lot in survival analysis, and I will not elaborate further. But in most EPI study, we deal mainly with right censoring, especially in cohort study where follow-up ends before all event occurs. So in survival analysis, the outcome is not simply, as we said, whether an event occurs, but the time until that event. This could be time to death, time to disease onset, or even time to recovery. So this type of data is used across many fields, including medicine, engineering, and social sciences. And the key distinction is that we are modeling time to event rather than just the occurrence of the event. There are three main objectives in survival analysis. So we can estimate, first, to estimate the time to event for a group, a cohort group. For instance, MI patients are followed up when they had their first MI, and we are following up all the patients to see what would be the time until second heart attack. So we're looking at overall the experience of the MI patient. Another objective would be to compare the survival of those MI patients between different groups. For instance, we can compare male and female and look at the time to second heart attack, and instead of taking the overall experience of the whole cohort. And third is to assess the effect of multiple variables over survival time. For instance, we can look at whether weight, insulin resistance, cholesterol, and other factors influence survival time of MI patient simultaneously. So this required actually an analysis, a regression analysis that is very specific to survival analysis. Okay. So, and these objectives, they guide the choice of the methods we use, such as Kaplan-Meier for estimation of the curve and Cox regression for multivariable analysis. So you might wonder why we cannot simply calculate the mean time to the event. Okay, so the problem is that censored observations do not reflect the true time. So averaging them might have some issues. Similarly, we can think about why not treat the outcome as binary, such as whether the event occurred or not. However, this also ignores the timing of the event. So therefore, we need a method that really incorporates. But anyway, before we think about what's the new method, so let's look at the sample of 3 patients who are followed up over time after their first myocardial infarction to look at the time for their second heart attack. So the first patient here experienced the event after 5 years. So he enters in 1990 and had the event in 1995. So we observed the event. Okay. Patient 2 enters in 1991 and drops out in 1997. So the second is lost to follow up after 6 years without the event. This is a censored observation. And the third entered in 1993 and then still alive at the end of the study. The end of the study is 2000, and this means that patient 3 is still without the outcome after 7 years. This patient is also censored, and this kind of data structure is exactly why survival analysis is needed. So let's understand the data, and here we summarize the same data we're talking about. So patient 1 has a known event time, 5 years, and the 2 others are censored, so we don't know the event time. And when you see a plus, this means that they are censored. Okay, we call them censored observation. We know that they remained event-free up to a certain time, up to 6 months, 6 years. The patient 2 did not have the event. Up to 7 years, also the third one did not have the event. So the challenge is to incorporate both complete and incomplete observation in a valid way, and this is really what survival analysis. But if we try to compute the mean time to event, let's see what happens. So we add up the years and we average. Okay, so the average will systematically underestimate the true average survival time, right? Because we don't know how long will they stay without the event. So the 6 and the 7 actually are underestimate of the time to second heart attack. Okay, so instead, if we simplify the outcome up to a binary variable, event versus no event, so we lose important information. When we do that, it means that we are considering those who are censored as non-event. So two groups may have the same proportion of event, but the timing of those events may be very different. So let's take this example where we are comparing two different chemotherapy treatment for patients with a certain cancer. And cancer patients were taking one of two treatments, and then we follow them up either until death or until year 2000, whichever occurred first. So this is again a hypothetical example. So at the end of the study, 40% of the patients in each of the two chemotherapy had died, exactly the same proportion. It means that there is no difference between the two chemotherapy group, right? Neither treatment is superior. However, when we look further into the study, the data, we realized that the 40% who died within the first chemotherapy group, 40% died within the first year of after first year of treatment. While the second group, and the other 40% who took the chemotherapy too, they died. The 40% died, but they died between 5 to 6 years after stopping the treatment. So therefore, the timing of the event was different, even though the percentages were similar. So what we need is a method that combines both aspects, the occurrence of the event, this binary yes-no event, and the timing of the event. It should also handle censoring very properly and make use of all the available information that we have, like the timing when the people are lost to follow up, or when how much they contributed under observation. And this is exactly what survival analysis method do. And one of the key output is the survival curve. So the survival curve is a central concept in survival analysis. It represents the probability of surviving or remaining event-free up to a given time. Okay, so this is so at any point in time t. Okay, ST tells us the proportion of individuals who have not yet experienced the event. So this is the t. This is the t always as the x-axis. So at this point in time, what would be the probability that people are still free of the disease? And this provides a dynamic view of how risk evolves over time. So here we visualize the survival function ST over time. So at the start of the study, again, it is everyone survival equal 1. Everyone is free of the event, since no one has experienced the event yet. And as time progresses and events occur, the curve decreases. And this curve summarizes the entire survival experience of the population. This is when the survival curve sometimes does not decrease. It might stay also the same, or it might decrease, but it will never increase, because this is because once an event occurs, that individual is no longer at risk. So the curve reflects a cumulative process over time. In many studies, the survival curve does not reach zeros. This happens when not all participants experience the event during the study period. Some remain censored, meaning they are still event-free at the end of the follow-up study. Okay, there are two main approaches to estimating survival. Kaplan-Meier, which was developed in 1958, it estimates the survival when the data are ungrouped. It means that we know the exact surviving time of each participant, and usually when the sample size are small, the cohort is small, but it can still be done on large cohort. And we have the life table. Also, it produced the same survival, but this is used when data is grouped into intervals. It means that we don't know exactly the time of the event. Anyway, in both methods, the probability of surviving any length of time t from the beginning of the study is a cumulative probability. So we calculate at each point in time, we calculate the probability of surviving that interval or that time, and then we multiply it by the previous probabilities. And this creates a cumulative survival function over time. So what's the data structure for survival analysis? Each individual has to have two key pieces of information. First is the time variable, which represents either the time to the event or the time to censoring. Okay? Time at least disease-free or time at event. Second is the event indicator, which tells us whether the event actually occurred or not. And the simple structure allows us to apply survival analysis methods effectively. This slide introduces a real data set used to calculate Kaplan-Meier estimate. As we said, there's Kaplan-Meier or life table, but we will be focusing on Kaplan-Meier in this in survival analysis for this course. So the example, the data are from 12 hemophiliac patients. They're under at the time of their HIV conversion. So they were diagnosed with AIDS, and then how long does it take them to convert? And we have the exact time, like 2, 5, 6, 17, 16, 16, while the other one are the censored, the time where the observation were censored. It means that either they lost to follow up or the study ended and we're not able to see any event. So this is usually when it is censored, it's indicated by plus sign. So the goal is to use this information to estimate the survival probability at different points in time. So this is the Kaplan-Meier method. It starts always with survival equal to 1. So everyone has not yet experienced the event. And after starting at time 0, the curve can be estimated at each time of the event, but not at censoring time. So if we have people who converted at 2 months, 6 months, 7 months, so anything that does not have a plus, this is the time of the event. So we calculate the probability of survival only when we have an event. And so what we do at each event time, we have the number, we update the number of individuals who are at risk and the number of events. And the survival would be the number who are at risk minus the number of events over the number of events. So this is the probability, and we calculate by the previous probability to have a cumulative probability distribution. So this is proportion of original sample making it to time t. So therefore ST is making it to time t and above. So this is and beyond. Okay, so as we said, curve will be estimated at each event, but not at censoring time. So let's take the first event. So the first event happened at 2 months. How many were at risk? We had 12 at risk, and we had 1 event at month 2. So therefore, the probability of survival is 12 minus 1, the event, over 12. And this is 11 over 12. This is 0.92. So this is the first event. We don't have any other probability before it. So 92% have survived month 2 and beyond. Of course, from this, if I can tell you what's the probability of the event, the probability of having the event is actually 1 out of 12. Okay. Probability of surviving the event is 12 minus 1 over 12. So this is probability of surviving, and this is probability of having the event. But the curve is about probability of survival. So therefore, it is 12 minus 1 over 12, that's 22. So we take the second. As I noted, at 3, we don't calculate any probability because we don't have the event. We don't know if the event happened. So therefore, we skip to the 6, where 2 events occur at month 6. So survival at time 6 and beyond is the survival. This is survival at time 6, which is how many were at risk minus how many events over how many have survived, times the previous one, multiplied by the previous probability. So what is probability of survival? How many were now at risk? We already lost the 2. Is not anymore at risk at 2 months. The one that is censored, so therefore these remained at risk, which are 10. And out of them, 2 develop the event. So therefore, the probability of surviving is 10 minus 2 over 10 times the probability of surviving up to month 6. So therefore, it's this component, 0.80 times 0.92. 0.72 is the probability of surviving up to month 6 and beyond. And again, if I ask you what's the probability of surviving month 6, so this is 2 out of 10. All right, so this is probability of having the event, this is probability of surviving the event. Okay, so this is another one. Again, after month 6 we have one censored. This censored is already its experience was taken into consideration in the previous probability. So therefore at month 10, how many are at risk? These are the people at risk, which are 7, including the 10. And how many event happened in this among those 7? 1. So therefore, at month 10, I have 7 at risk. I have one event, which is this one, the red, over 7, which times the previous probability. So it's 0.86 of this one, times 0.74. It's 64% have survived months 10 and beyond. Again, what's the probability of having an event at month 10 is 1 out of 7. So this is the probability of the event, and this is probability of surviving the event. This is surviving, and this is having the event. Okay, and when we do all the survival probability, this is what we get. And this example, the last observation, so everyone has converted, so all the hemophiliac has converted, and therefore the survival curve will reach eventually the 0. Okay, but as we said, and not all curve reach the 0, because some of the not all the participant experience the event, the curve might not reach a 0, and this is something that we have already discussed before. So therefore, what's this Kaplan-Meier curve? The Kaplan-Meier is built step by step at each observed event time, at 2, at 6, at 10, if you recall. We don't estimate survival time at censoring time again, but censoring time still affect the number at risk, right? Because we consider them at risk when we have an event. And the stepwise approach is what gives the curve its characteristic shape. Okay, so this is an example a real example of a survival curve. This is a group of patients who had CABG surgery, and we're looking at their survival. And then we compare their survival based on whether they have diabetes, renal failure, peripheral vascular disease, or both. And then we see, so Awashi first, as we said, it's a step function. It drops at each event. Every time there is an event, the curve drops. And then we see here, every curve is an overall experience of the people who have all these characteristics, only diabetes. And we see that the best survival curve is when people have diabetes, and the worst survival is when they have all these risk factors. And if you notice, there is a test called log rank test. This is a test that we will be talking about in a minute, which tells me whether the survival experience is different among the 4 or the 5 groups. And with a p less than 0.001, it means that there is a statistically significant difference in survival among the 5 different groups. That's captured by the log rank, but we don't know the magnitude of the difference. We only know that there is a difference, and graphically we can interpret that difference. This is another illustration for Kaplan-Meier estimate of survival curve. We have 10 people. Again, we have 10 observation. The 10 observation, what we have is the time to the event. Whenever we have a plus, it means censored. It means that we did not observe the event. And when we don't have a plus, it means there is an event at time 6, at time 8, at times another one at time 6, one at times 4. And then, as we said, plus is censored observation. The first thing we do is we order the survival time, and then we calculate the probability of surviving at least at time t or beyond. So therefore, the first event occurred at time 3. So the survival at time 3 and beyond is 9/10 because we have one event that happened out of 9, and therefore what the number that remained are 9/10, which is 0.9. And then at 4, we move at 4. How many are left? So now we have 9 that are left at risk. So these are at risk at 4. Okay, so 4, and how many event is 1? So 1 out of 9, it means that the proportion that survived is 8 out of 9. And to look at the proportion that survived beyond 4, at 4 and beyond, it's provided they have survived 3, which is 0.9 times 0.8/9. So on and so forth. So the censored individual are entered in earlier probability and are not included in later conditional probability. And what you see here is a detailed calculation behind the Kaplan-Meier estimate of the last illustration I showed you. So at each point in time, we track the number at risk, the number who have the event, here are death, how many are censored, and then we calculate the probability of the event, the probability of surviving the event, and then the cumulative probability, which is the survival. So as I showed you before, at 3 months I have one event. So how many, what's the probability of the event is 1/10. What's the probability of surviving? Because this is all about survival, is 9/10. So 0.90. At month 4, I have another one, and I don't have any in between, any censoring. So the number again of probability of death at month 4 is 1/9. 9 because we already lost one. It's 8/9. So what's probability of survival is 8/9. Sorry, 1/9 is probability of dying at 4. 8/9 is surviving. So therefore, probability of survival at time 4 and beyond is 0.89 times the earlier probability. And then so on and so forth. As you see that all the probability of survival, the cumulative, are only calculated when we have an event. Okay, like any statistical method, Kaplan-Meier relies on several assumptions. One important assumption is that censoring is independent of survival, meaning that those who lost to follow-up have the same survival prospect as those who remain. This is the second one. Another assumption is that survival probability are consistent over time, meaning early and late recruit have similar risk. Okay, so whether you, let's say, if you have a long follow-up, so probability whether you survive 3 months at the beginning or survive 3 months at the end should be the same. So unless there's really a major treatment, a major event that changed the risk of the disease, then this would not be true. So anyway, violation of this assumption can bias the survival estimate. They should be considered. So every time when you do your survival analysis, you should at least think about them and see whether they hold true or not. And they are the same for the life table. So to summarize the Kaplan-Meier method, we first order the survival data. We then calculate survival probability at each event time. And finally, we multiply these probabilities to obtain the cumulative survival curve. Importantly, those calculations are done only at event time, not censoring time. And this method provides a simple yet very powerful way to estimate survival over time without making strong assumptions about the underlying distribution. Okay, so in addition to the survival curve, so you see how people are surviving and how the survival curve is decreasing. We often summarize survival using key statistics. One of those important measures is the median survival time. Median meaning that the time at which 50% of the population has experienced the event. And then you see, so this is usually used by clinicians when they report survival after cancer being diagnosed or after a certain disease being treated. So they would tell their patient that the median survival time is, it means that 50% of those people similar to you who have the disease or who have taken that medication would survive free, or would, depends of course what event we are looking for. We may also report 24, so 2 years, or 12, 1 year. Okay, so this is usually what people mostly use: 1 year survival, 5 year survival, 2 year survival, or median survival. So these summaries help simplify interpretation, but again, they don't capture the full shape uh, of the curve, okay, of the survival curve. So this is again, it illustrates how median is derived from the curve, from the survival curve. So from the, here is the y-axis, and this is the cumulative percent, and then you extend a horizontal line from the 50% to the curve, and then you calculate, this is the median time. But again, you can take any time from the x-axis and look at its probability of surviving. So if I want to look at, let's say, at 36, here it's 0, so I can look at here and then extend a horizontal line to look at what is the proportion surviving up to here, for instance, 31. Okay, so we can do it either way. And we can also look at every time the event occur, which are those uh, drops. You can look and have a confidence interval built around it. But the issue is that those dotted line here are the confidence interval around the probability. So probability at every time. But this could be really very cumbersome and too many numbers to read. This slides present the life table method, which is an alternative to Kaplan-Meier when data is grouped into intervals. So instead of looking at every person's exact time of experiencing the event, we're looking at an interval of time. And here, but the difference is that we calculate something called effective and at risk. And this effective and at risk, if you look down, it is the number who are at risk here in terms of the absolute number at risk minus half the censored, because we don't know exactly when the censored happened. For instance, I will take the first example. In between 0 and 1, we had 2 people, so we started with 200 people who were at risk of the death, okay, which is the event. During that interval, 22 died. And we know that during the interval 0 to 1, we had 8 that were censored. So most likely they dropped out before knowing whether they're going to develop the event, the 8. So what would be the number, effective number at risk? It will be 200 minus half the 8. So 200 minus half the 8 is 4. So therefore 196. And therefore the probability of dying is 22 over 196. And the probability of surviving is 200 minus 22 over 196. Sorry, it's 100, excuse me, it's 196 minus 22 over 196. So we're always considering the effective number at risk. I go to the second one. So to get to interval 1 to 2, we already lost 22. We lost as well 8, right? So these are 30 already lost, 170. All right, so 170 are lost in terms of the participant. During that follow-up period, we have 38 that died. So this is that died. So these developed the event, and 12 they were censored. So therefore, what would be the effective number at risk? It will be 170 minus half those who are censored, which is 6. So therefore, the probability of surviving is 38 over 164. And probability of surviving is 164 minus 38 over 164. So we're talking always about the effective risk. So far we have focused on estimating survival curve. Now we move to statistical inference, specifically how to compare survival between groups, as you've seen for those patients with cabbage surgery, and how we compare those with diabetes to those who have other risk factors. So the key question becomes, are the survival experience of these groups significantly different? So one approach is to compare survival curve at specific time points, but this can be inefficient and arbitrary. What I mean is that taking for instance, time point, the first event that occurred at month 3, and compare that probability between 2 groups or 3 groups. And this is really cumbersome, and to take all the specific time point when the event occurs. So instead, we use statistical tests that compare the entire survival experience across all the time points rather than specific time points. And the most commonly used tests are the log-rank test and the generalized Wilcoxon test. There's a Breslow and Jehan. And then both compare the survival curve across multiple time points. And the question is to have a null hypothesis that the survival functions are equal between the group, 2 or 3 groups, and the alternative hypothesis is that they differ, and these tests evaluate differences across the entire follow-up period rather than at a single point in time. So this is a real example where Kaplan-Meier curves were compared with confidence interval. The overlapping confidence interval denotes no significant differences, but this is not always reliable for formal comparison. So this is like at every point in time where we have an event, and the event is to have motion sickness. If people have a low level of vertical motion while doing an aviation simulation versus those who have a high level of vertical motion. And it's too much to compare, as you see, and you don't really capture and be able to capture what's really the experience and the difference between the two groups. So two common statistical tests for comparing survival experiences in groups are the log-rank test and the Wilcoxon test. The way they work is that we compare the observed number of events in each group to what would be expected under assumption of no difference. And if the observed and expected values differ substantially, the test statistics, whether log-rank or Wilcoxon, becomes large, leading to rejection of the null hypothesis. And this allows us to conclude whether survival differs significantly between groups. The log-rank test is more sensitive to differences that occur later in time among or between the groups, while the Wilcoxon test actually captures more early differences or gives more weight to early differences. Both tests provide a p-value but do not estimate the magnitude of the effect. I mean, there is no relative risk. It's not a measure of association. It's only whether the overall experience are statistically significant differ by groups. So this slide provides a visual illustration of comparing survival curve. This is a group of patients, and we are following them up to see how many will remain TB-free. So this is TB-free survival population. On the figure to the right, we are comparing patient. One of the group, which is the dotted group, is the people who are stage 1 or stage 2 or have high CD4 cell count, while the second group is the more serious group. This is the one which is the one with CD4 cell less than 100, and they are advanced stages of the disease. And you see that the survival here is really worse. But if we want to see whether this is statistically significant, we do a log-rank test. And they say here the p-value comes from a log-rank test, and this is p less than 0.001. It means that the difference in survival that we see between these two groups of patients is statistically significant, and this is very similar also to the graph that we see to the left of the slide. So in the previous slide, we have compared groups, but what if we want to adjust for multiple variables? So this is where Cox regression comes in. It allows us to assess the effect of several factors simultaneously on time to event while accounting for censoring. So in Cox regression, results are expressed as hazard ratios. So the beta, the coefficient, is a hazard ratio, which represent the relative risk of experiencing the event at any given time. But again, it depends on survival data. It means that the data structure, I need to have the event and the time people remain free until the event, or the censoring, whether they were censored or not, and whether they had the event. So a value greater than 1, again, for the hazard indicates higher risk, while a value less than 1 suggests a protective effect. And this model is widely used because it does not require specifying the baseline hazard function. But you have to really know and understand the hazard concept, which represent an instantaneous risk of the event at a given time, conditional on surviving up to that time. It differs from the cumulative risk because it focuses on the immediate risk rather than overall probability. And it is important to understand hazard uh, uh, to be able to interpret Cox regression result. But in any case, a hazard rate ratio is a relative risk. It's a measure of association when data have the structure of a survival analysis. This is an illustration of Cox regression analyses. This is using the same example, the free tuberculosis, so it's survival until people get tuberculosis, taking into consideration the stage of the disease, the CD4 cells, the viral load, and other. So in the first line, we have unadjusted relative risk, which are the hazard rate ratio that the Cox regression generates. And the hazard rate ratio, or the relative risk for age alone, I mean, when we only put in the Cox regression age, it is statistically significantly associated with having TB, so it's a hazard of TB, not surviving TB, but having TB. It's 2.23 significant, and when we add the 4 other variables, it becomes 286, so there was a negative confounding. When we remove the confounder, it becomes stronger, the association, and significant. And other adjusted hazard rate ratio or final result are past history of tuberculosis associated with 0.07 is not significant, or we'll skip that. The CD4 cell count, so if we have a lower CD4 cell count compared to higher, is associated with TB and significant. And finally, if a patient have an advanced stage of the disease, stage 3 and 4, it's also significantly associated. So this is what Cox regression produces with confidence interval and p-values. So final takeaway message is that survival analysis is essential when studying time to event data. The traditional method, like the linear regression, looking at only mean time, or logistic regression, considering only whether the event occurred or not, have numerous limitations, especially when we have data that have a lot of loss to follow up, because we don't account for censoring. So that's why we do a time to event analysis. So the Kleppler-Meyer allows us to estimate the survival curve, while the log-rank test compared groups. Cox regression extends this by allowing multivariable analyses, and these methods really provide a comprehensive framework for analyzing survival data. What is it required for survival data? We require a specified two-state non-recurrent event. So we need to have an event that happens, which is not a recurrent event. We need a relevant metric of time. We need the time from time 0 to the entry time, and from the entry time to the exit time. The exit time could be when we have the event. The exit time could be when the study finishes. The exit time could be when people are lost to follow up. We assume random censoring, meaning that censoring happens independent of survival, and then we build upon assembly of risk sets. So at every time, what we mean by risk set, that every time an event occurs, we calculate a probability of survival, and then we add them up, and we do the cumulative survival curve. And that's it, and please consider this as a very introductory lecture on survival analysis.